There are a huge number of medical applications for ideas flowing from physics, and to be honest, the number is growing all of the time. Here, we'll consider a small number of the techniques you will certainly encounter during your medical career. X-rays have been in use in medicine for over 100 years, but the resolution and structure we can see using them has developed markedly. And today's CT scans provide really an undreamt of level of detail compared to only a few decades ago. Now, of course, X-rays are simply a very high energy part of the electromagnetic spectrum. And as such, all of the ideas we saw with light rays can also apply to X-rays, meaning that they can be reflected, refracted, diffracted, just as visible light can. As you can see, X-rays have very high frequencies and so very short wavelengths, as we would expect for such high energy radiation. Also, the equations which relate to the electromagnetic spectrum also apply to X-rays, including the wave equation shown here, where c is the speed of light, f is the frequency of the X-rays, and lambda is their wavelength. This provides an ideal opportunity on the exam to ask you to substitute values and find an unknown quantity, and we've seen this previously. The key thing here, though, is to recognise that if the frequency of the radiation f is large, this must mean the wavelength of the radiation lambda must be small. There's an inverse relationship between them. Now, X-rays are generated by firing high-energy electrons towards a tungsten target. When the electrons hit the target, some of them generate X-rays, according to the equation shown here, where E is the charge on an electron, V is the voltage the electrons are excited through, H is a constant called the Planck's constant, and F is the frequency of the X-rays that are produced. Now, you could of course be asked to use this equation in the exam by inserting appropriate values, and some examples of this type of usage are given in the study guides. Here though, we just want to highlight the key idea of the equation, which is that a larger accelerating voltage will produce higher frequency X-rays. And what about the wavelength of the X-rays produced? Well, look at the two equations we have here. We can actually combine these two equations by substituting the first equation for frequency into the second equation, giving us this combined equation. Again, the exam might ask you to use this equation given some values, but the key point of interest is that as the accelerating voltage V increases, then the wavelength, lambda, of the X-rays must decrease. This is of course what we would expect, as we know the frequency and the wavelength are inversely related. Now, X-rays are good at passing through materials, and it's this that makes them useful in medicine. They really easily pass through our soft tissues, but they can be stopped by denser materials such as bone. This is actually how X-ray images, such as the one shown here of the knee, are formed. Now, as they pass through a material, the intensity of X-rays will fall, and we call this process attenuation. The degree to which attenuation occurs will depend on two things: the thickness of the material X and a quantity called the linear attenuation coefficient of the material, given by the symbol mu. And as you might have expected, or maybe feared, there's an equation which relates the initial intensity of the X-rays, here I0, with the new intensity of X-rays after they've passed through a material, given here as I. Here it is. Now, if this equation fills you with dread, don't worry. The key is to see that as the thickness of the material X increases, then I will become smaller. In other words, less X-rays get through a thicker bone. And also, the larger the value of the linear attenuation coefficient mu, then the less X-rays will penetrate the material. Now, this might of course be a good point to review your work on natural logs if this doesn't seem clear. Another key diagnostic technique you're going to encounter is ultrasound. And let's consider this now. Ultrasound uses high-frequency sound waves to produce an image of structures within the body. Perhaps the most common example is the use of ultrasound in prenatal care to image the fetus as it grows. The way it works is this. A transducer produces sound waves, which are harmless to the mother and child, and pass through the soft tissue. However, at any boundary between different types of tissues, some of the sound waves are reflected and they bounce back. And these are then detected and can be used to form an image of the fetus, as I've shown here. Now, ultrasound works because sound waves hit boundaries between different tissues, and some tissues are better at reflecting sound waves than others. The degree to which sound waves are reflected depends on a very specific property of the tissue, called the acoustic impedance. On screen are some different tissues and their associated acoustic impedance values. Now, obviously, don't worry about learning these values, but take a look at their magnitudes. Now, for sound waves to be reflected and so produce an image, we really need the difference in the impedance values of the two tissues to be small. If the difference is too large, we find all of the sound waves are reflected, and so none of them pass into the deeper tissues. However, if they're too similar, then there's no reflection, and so we can't see the boundary image at all. This is why ultrasound cannot be used to image bones. As the sound waves pass from the muscle into the bone, the difference in impedance, as you can see, is very large. This means nearly all of the sound energy is reflected from the boundary, and so none of it passes into the bone, meaning the bone cannot be imaged. It also means, of course, that the brain, which is encased in the skull, can also not be imaged using ultrasound. Finally, you may have noticed a problem with using ultrasound. As you can see, the impedance values for air and pretty much any tissue, such as blood, have extremely different magnitudes. And this means that if there's any air between the transducer and the skin, all of the sound waves are going to be reflected, meaning, of course, we won't be able to form an image. So, how do we prevent this? The answer, as anyone who's had an ultrasound knows, is that a jelly is first applied to the skin before the ultrasound is taken. Now, this has a very similar impedance to the skin, and so allows the sound waves to travel into the body. It's also worth mentioning that air in the body can be a major problem when taking images of deep tissues, as it again prevents the sound waves passing through. So, in summary, there are a vast range of applications of physics in medicine. Today's X-rays and CT scans provide extraordinary levels of detail for clinicians. X-rays are high energy and so can be damaging. Materials absorb X-rays according to their linear attenuation coefficients. Ultrasound uses high-frequency sound waves to form images, and sound waves are reflected according to the impedance of different tissues. And to see deep structures in the body, air must be avoided at all costs.